In this video, we continue exploring reactions of carboxylic acid derivatives such as esters and amides. Here we'll be exploring reduction reactions where we are going to be, as a result of the reduction reaction, which will lower the number of bonds between carbon and an electronegative atom, we are going to, in these reduction reactions, be removing the carbonyl group in each of these cases. There are some differences between reduction of esters versus amides, as we will get into when we look through the mechanism for each of these. One thing that is similar between them is that in both cases we use lithium aluminum hydride as our reducing agent. So we are going to explore the mechanism for reduction of an ester, such as the structure they have in the highlighted left side of the screen right now, where we have an O-alkyl group as a leaving group here. And ultimately, by treating with a reducing agent, we're going to yield alcohol products. Whereas with an amide, when we treat with a reducing agent, we are going to yield an amine product. So let's take a look at the mechanisms for these reactions and go through the rationale for how we create the products of these reactions, tying some similar themes to the nucleophilic acyl substitution reactions under basic conditions that we've looked at before, since we can think of this reducing agent as being one that functions under basic conditions. We don't have acid present here, and we think of this as being a hydride donor, is the way that lithium aluminum hydride has been described before. When we say a hydride donor, what it means is we're donating hydrogen with a lone pair of electrons associated with it, making that a basic anionic nucleophile situation. So looking at this for the particular scenario of ester reduction, we'll go through the general mechanism for this particular reaction, and I'm going to do this mechanism for a specific example of, let's start here with methyl acetate. So we need a methyl group directly bonded to the oxygen there. And acetate is our 2-carbon chain with the carbonyl, so we start with methyl acetate. We're going to react with our lithium aluminum hydride, which we can draw out in detail here as Li, lithium cation, which is complexed with the AlH4, so I'll go ahead and draw out that. And the bond between the hydrogens and the aluminums is polarized such that the hydrogen we could think of as possessing the electrons from this covalent bond here, allowing that hydrogen to act as a hydride, like it has a lone pair of electrons on the hydrogen atom there. Now, as we do this, the way that we can show this reaction mechanism rigorously is we think of the hydrogen as possessing those 2 electrons from the bond that I've shown in red. That's going to come over, and it's going to attack the carbonyl carbon of our methyl acetate. As we do that, the pi electrons from methyl acetate are going to come up, and those are actually going to help to stabilize the aluminum by coming over and forming a bond to that aluminum in this particular mechanism. So let's go ahead and show what results from that. So we'll create our product here. We have our carbon that was our carbonyl carbon that I'm going to highlight in pink here on the reactant side and product side. It was directly bonded to a methyl group, which we'll show here. It was directly bonded to the O-alkyl group, which I will also go ahead and fill in as our O-methyl group there. And then additionally, we will create a new bond between this carbon and the hydrogen that we see over here, because we have the hydride come in and attack that carbonyl carbon to create a new carbon-hydrogen bond. I'll show that new carbon-hydrogen bond there in red to follow the electron pushing arrow that we showed, having the hydrogen coming in and attacking that carbon. And then what was our carbonyl electrons have come over and attacked the aluminum to allow us to form a bond between the oxygen atom and the aluminum of the AlCl3. So I'll go ahead and show that as well as a bond here between the carbon and oxygen. And then that oxygen atom that was part of the carbonyl to start with now has formed a bond to the aluminum, and the aluminum has 3 hydrogens still bonded to it that we can see like so. Now, keep in mind, there is one thing that I did not show in our lithium aluminum hydride. That is the aluminum with 4 covalent bonds will have a negative charge. So I should go ahead and put that in. Negative charge for the aluminum with 4 covalent bonds to start with. Aluminum over here has 4 covalent bonds as well, so it still has a negative formal charge. Dotting all my I's and crossing all my T's, I'm going to fill in my lone pair electrons on the oxygen atoms like so. And that is our intermediate that we have here. So the first step of this mechanism is that the lithium aluminum hydride attacks the carbonyl. That is really the essential part of this, is with this hydride coming in and forming a new hydrogen-carbon bond right here. That's what's carrying out the reduction, because we're going to be replacing a carbon-oxygen bond with a carbon-hydrogen bond here, creating this carbon-hydrogen bond in our product side. And then at this point, what is going to happen is that we will reform the carbonyl as the leaving group leaves. So far looking very, very much like a nucleophilic acyl substitution reaction, where the first step was that the hydride acts as our nucleophile. We can think of that as behaving like an anionic nucleophile, attacking the positively polarized carbonyl. That's straight out of the playbook of our basic nucleophilic acyl substitution reaction. Second thing, also straight out of that playbook, which is that the carbonyl reforms as the leaving group leaves. So in this particular case, here's how we'll show the leaving group leaving as the carbonyl reforms. We have this situation where the oxygen bonded to the aluminum. So it's actually going to be this bond between oxygen and aluminum that breaks in order to enable the carbonyl group to reform, because we need to get rid of that aluminum. So what's going to happen is we take the electrons in that oxygen-aluminum bond, we bring those down to remake the carbonyl group. At the same time that happens, our heteroatom here, the oxygen has to break away, like so. Now we'll go ahead and write out what results from that. So we will have reformed the carbonyl, and we will have bonded that a hydrogen and a carbon. Our leaving group, O-methyl, which I'll abbreviate as OME for methyl group, will have left like so, giving us this as our product of the reaction. So what we've done here, just to highlight our key components here, is we reformed the carbonyl. That became the carbonyl down here that I have highlighted in yellow. Additionally, we had this methyl group here that was bonded to the carbonyl, so that's the methyl group here in green. And then thirdly, we had, which I'm highlighting in red here, the hydrogen atom, which is the hydrogen atom that we see in the product down below. We also could go ahead and write out to dot all our I's and cross all our T's here that we've created as a result of this AlH3 as well from this reaction. So now that we have accomplished this, we've created as our product an aldehyde. And the aldehyde, we know, can be reduced with lithium aluminum hydride. We've seen that before. So we can break this down into kind of two different chapters, if you will. The first chapter here that I'm highlighting in green was our nucleophilic acyl substitution. Because what we were doing was we were replacing the O-alkyl leaving group with a new bond to hydrogen. When we relate the methyl acetate starting material to the aldehyde product, that's what's happened, is our O-alkyl leaving group has left and it's been replaced with a hydrogen nucleophile, making this fit that definition of nucleophilic acyl substitution and very much following the general reaction mechanism that we've seen time and time again. Now that we've created an aldehyde product, we have created a product that can further react. And so what's going to happen then is that that aldehyde is going to be further reduced using the general reaction that we have seen previously for reduction of aldehydes and ketones. So that aldehyde product that we created by reducing the ester is going to continue onward because it is very reactive with lithium aluminum hydride as well. So I'm going to go ahead and plug in my business end of lithium aluminum hydride, which is the ALH4 portion. So I've got my AlH4, negative charge on the aluminum. And what will happen here is that that aluminum hydrogen bond will break, allowing the hydrogen to act as a hydride, come in and attack the carbonyl carbon, which is electrophilic. And that is going to force that carbonyl group to go somewhere. The electrons from that are going to come in and attack the aluminum. Much like what we saw up here in our first step of the nucleophilic acyl substitution reaction. Same sort of electron pushing errors where the hydride comes in and attacks the carbonyl as the electrons from the carbon-oxygen double bond come over and attack the aluminum. Same sort of thing occurring down here. So this is our first step of this particular mechanism of reducing the aldehyde, is that the hydride nucleophile attacks the carbonyl. So we'll go ahead and write out the product of that step, which is where we'll now have an oxygen with a single bond to the carbon. I'm going to put the carbon atom there that was the carbonyl in red. Now it's this tetrahedral carbon on the product side is what it's become. The hydrogen atoms will be here and here. One of those is a new carbon-hydrogen bond. I'll show that new carbon-hydrogen bond in red here, and the hydrogen that we just donated in red, that was donated from our aluminum hydride. And our oxygen atom technically shouldn't really be oxygen anion because we showed it forming a link to the aluminum. So to be completely accurate here, the most accurate way to show this is to have that oxygen atom linked to the aluminum, because that's going to help stabilize the aluminum. So we have AlH3 here, negative charge on the aluminum. And then onward from there, what's going to happen as step 2 of this reduction reaction is that this will wait around like so in solution until we add acid. And when we add acid, what the acid is going to do is enable protonation of the oxygen to give the alcohol group that we see in the final product. So I bring in my acid, which we have to add as a separate second reagent here after the lithium aluminum hydride has done its job. And what will happen there is that the electrons from the oxygen aluminum bond come in, attack that proton. That forces the aluminum oxygen bond to break, replacing the oxygen aluminum bond with an oxygen hydrogen bond, giving us an alcohol as our final product of this reaction. I'm going to write that alcohol product over here in bold. We'd have our hydrogen here, and our OH group then in our final product. I'll go ahead and circle that as well, just to emphasize what our final product is there. So all we've done in this last step is we brought in this proton that we see donated from adding a source of dilute acid to the reaction mixture, because this intermediate here is quite basic, quite eager to react. And in that reaction with an acid, we're going to take these electrons from the aluminum oxygen bond, break that aluminum oxygen bond, take the electrons over to grab the proton that becomes attached to the oxygen in the final product. So when we reduce an ester, we will yield an alcohol product. You will note that this alcohol product we've created corresponds to the carbonyl group of our starting material methyl acetate in the upper left corner, as well as the R group that's directly attached to it to the left of it that I'm highlighting here in our starting material in the upper left corner of the screen. So highlighting what corresponds to our final product that we've drawn out here, our carbonyl group from our starting material methyl acetate became an OH group, and then we had our O-alkyl group over here as well. So that's this O-alkyl group here and the final yellow product, OH group like so. Now what happened to the leaving group here, our O-methyl group, in our starting structure from methyl acetate in the upper left corner? I'm highlighting that leaving group right here. What happened to that? Well, we can trace that out along the way. Where did that go? Okay, well, it left at this point. And so what happens then is that hangs out in solution as well. And then once acid is added to the reaction mixture, that too is going to pick up a proton, because that is quite basic, being that it has that negative formal charge. So once you add the source of proton, it's going to pick up that proton to become methanol CH3OH. So if we are truly to account for all of the carbon atoms that were in our starting material, carrying those all the way through to the product. To account for all of them, we are keeping in mind that the carbonyl of the methyl acetate is reduced to a hydroxy group in the final product. The leaving group has left, and then ultimately that leaving group oxygen here gets protonated to give us a final product where we've conserved the total number of carbon atoms that were in our starting material all the way through to our product. So if you're in a situation where you're asked to show the product of reducing an ester, the product of reducing an ester is always going to correspond taking, if we're reducing an ester, what we can deduce from this mechanism is that if we have an ester here as our starting structure, what will always happen in this reduction reaction is we will always have lithium aluminum hydride as our reducing agent. Then after that is totally reacted, then we add the acid as a second separate reaction. And what will happen during the course of this reaction as the total outcome is that this bond breaks because that O alkyl group is a good leaving group. And the carbonyl group here gets reduced on this side to give an alcohol group. The oxygen over here ultimately gets protonated, and therefore the products of this reaction are going to correspond to R, the carbon that was the carbonyl carbon, will be directly connected to the hydrogen atoms that are donated by hydride, and then an OH. And then on the other side, the O alkyl group here becomes protonated to give HOR prime. So we can always follow this template if we don't want to write out the total mechanism. We keep in mind that this is going to be the bond that breaks here. That leaving group will ultimately get protonated when we add the acid. And this carbonyl group here of the ester ultimately gets reduced via the addition of two hydrides to give CH2 and then OH. So that is our scheme for reducing an ester. Let's now take a look at what happens when we go to reduce an amide molecule. We'll see that the situation has some similarities and also some contrasts that we need to be aware of here in terms of the mechanism and the outcome of this reaction. So we're going to do reduction of an amide now. We will start with our amide starting material here. So we'll do here N-methyl acetamide, because we have that 2-carbon chain with the carbonyl, so that's where we get the acete part there. And we'll reduce with our lithium aluminum hydride. We're going to walk through the mechanism for how we go from starting material here to final product and look at how this mechanism and the outcome are similar to the reduction of an ester, and also how there are some key differences here that we need to be aware of and why those key differences exist. So let's go ahead and we'll plug in what's happening here first. So in this mechanism, the first things first is that when we react our amide with lithium aluminum hydride, the first thing that's going to happen is that the hydride attacks the carbonyl. So far, looking identical to the reduction of an ester in that we have our ALH4. Remembering my negative charge on the aluminum there, that has 4 covalent bonds. The hydrogen as a hydride, because it's taking the electrons from that hydrogen aluminum bond with it, is going to come in, attack the carbonyl group there. And then the carbonyl electrons right here that I'm highlighting in red in the carbonyl are going to come in, and they are going to form a bond with the aluminum to help stabilize the intermediate. So let's go ahead and show that product. So we'll have our oxygen. Our oxygen has formed a covalent bond to the aluminum, Al, and then the 3 hydrogens are still associated with it, so ALH3. The 4th hydrogen here was donated as a hydride to the carbonyl, so therefore we need a new bond between carbon and hydrogen. And we also have that bond between carbon and nitrogen right here, so we do that as an NH, and then our methyl group directly bonded there. And I will highlight in green here our carbonyl starting material, that carbonyl carbon becomes the carbon that we have in the product side right here. So now we have our oxygen directly bonded to the aluminum, oxygen ALH3. We have our hydride that's come in and formed a bond there, and we have our methyl group as well. And now, as we take a look at this, being sure to keep track of our formal charges, the aluminum there should have a negative charge since it has 4 covalent bonds to it. Now what's going to happen is that we would think, based on the template for the ester, that what would happen next is that this carbon-nitrogen bond would break, with nitrogen being the leaving group. Because normally what we have seen so far in these reactions is that the leaving group that breaks away is the heteroatom that was directly bonded to the carbonyl. But in this case, what's actually going to happen is that rather than the nitrogen breaking away as the leaving group, instead, the oxygen that's directly bonded to the aluminum is what's going to break away here. And why is that the case? We're going to break the oxygen because oxygen is a better leaving group than nitrogen. Why is oxygen a better leaving group than nitrogen? Oxygen is a better leaving group than nitrogen because oxygen is more electronegative, and so therefore, when you break this carbon-oxygen bond and take the electrons with it onto the oxygen to make a negative formal charged oxygen, that negative formal charged oxygen product is more stable than a negative charge on a nitrogen would be, because oxygen is more electronegative, so it's better able to handle that formal charge. So here's where things get weird compared to reducing an ester, is that in step 2 here of reducing an amide, the oxygen is what acts as the leaving group, and that oxygen is able to act as a leaving group because it's not just an oxygen by itself, it's bonded to that aluminum as well, which is going to help its cause. And so second step of the reaction here is that the oxygen bonded to the aluminum, OALH3 leaves, and we're going to form an imine group, a carbon-nitrogen double bond there. So let us show that carbon-nitrogen double bond formed by taking the lone pair of electrons to the nitrogen, bringing those down to make that carbon-nitrogen double bond, which will enable us to avoid making a positive charge on this carbon. Making a positive charge on the carbon is going to be inferior to making that carbon have a complete octet. So let's go ahead and do that. So we'll go ahead and make our carbon-nitrogen double bond there. Nitrogen is directly bonded to a methyl group still, so we'll draw that line to the methyl group. It's got a hydrogen bonded there. 4 bonds to the nitrogen is going to give it a positive formal charge. I will go ahead and, even though it's implied that it's there, I will draw that hydrogen in explicitly to just dot all my I's and cross all my T's here. So we have our hydrogen in red over here, and we can also show that that oxygen leaving group is broken away, so we have OALH3 there as our other product of that step. Now at this point, what will happen is that our carbon in our organic intermediate, this carbon right here that's directly bonded to the nitrogen, is electrophilic, because by resonance we could take this pi bond and we could move it onto the nitrogen to create a carbocation there and a second less stable resonance structure. But nonetheless, that helps justify that that carbon is electrophilic. And so what's going to happen here in step 3 is that the nucleophilic aluminum hydride, specifically the hydride part of that, is going to attack the carbon-nitrogen double bond. So let's show that occurring here. We'll go ahead and bring in our aluminum hydride, and I'm going to try to zoom out here just a little bit so that we can see what's happening. So in this reaction step, we bring in our ALH4, like so. And as we have seen previously, it's a good hydride donor, so it's going to donate that hydrogen with its lone pair of electrons, comes in, attacks the electrophilic carbonyl carbon there. In order to avoid going over the Tet rule, the pi electrons have to go back out onto the nitrogen like so, and that's going to give us our final organic product where we will have reduced the amide to give an amine product. So now we will have two hydrogens directly bonded to what was the carbonyl group, is now a CH2 group. And then our nitrogen out here will be NH with a methyl group and a lone pair of electrons. So we've taken the carbon that I've highlighted and I'm laser pointing in red in the upper right corner. We've had the hydride from aluminum hydride act as a nucleophile to come in and attack that carbon. That forces the pi bond to go out into the nitrogen, creating a new carbon-hydrogen bond here in the final product. Our new carbon-hydrogen bond is one of these ones in red. And we now have a carbon-nitrogen single bond. And due to the movement of those pi electrons out into the nitrogen, we have a lone pair on the nitrogen now in this final product. So what is essentially happening here, if you are tasked with showing the product of reducing an amide, and you are looking at it and you're going, what do I need to create as the product? Essentially, reducing an amide results in erasing the carbonyl group. The carbonyl group is replaced with the hydrogen atoms. So the net effect of reducing an amide is that you're going to replace the carbonyl group with two bonds between carbon and hydrogen. Those two bonds to hydrogen are donated from the hydride. We do that because of the fact that the nitrogen is a really poor leaving group. And so it's going to create a more stable pathway, a lower energy pathway through the reaction to have the oxygen leaving rather than the nitrogen leaving in this reaction mechanism, making this distinct from the ester reaction where we had an oxygen leaving group, and we were able to do this in more of a traditional nucleophilic acyl substitution route. So here, whenever you're reducing an amide, the take-home is get rid of the carbonyl, replace it with hydrogens to fill the octet for that particular carbon. That will give you the final product. We don't break that carbon-nitrogen bond because the nitrogen is not going to act as a very capable leaving group.